All right. Good evening, everyone. This evening we shall be looking at heat capacity and specific heat capacity. To start with, we are going to quickly consider the aspect of this topic that is the introductory part of it that we did in year 10. We briefly talk about that, and also we're going to look at some definition of terms. So from there we can connect it to what we are going to be looking at tonight. And basically we are going to be solving past questions from WAEC and NECO and probably UTME that are related to this topic. So just stay tuned and enjoy yourself. And at any point you think you have any question, the comment section is always open, so just drop your comment at the comment section. Drop your question at the comment section and the question will be attended to. If not during the class, even after the class, the question will still be attended to. And okay, to start with, we all know that heat energy is the energy that is transferred from hot object to cold object, and we can as well refer to it as a total energy of a body or an object. So, and you agree with me that heat energy is measured in joule because it's an energy, so it is measured in joule, and we measured it with a calorimeter. That is the equipment used in measuring heat. Okay, now let's quickly look at some other things. Heat quantity in an object, or quantity of heat in a body or an object, which is represented with Q, is directly proportional to the mass of the object. So what is the meaning of this? That is the quantity of heat that any object can hold is directly proportional to the mass of the object. The massive the object is, the more the heat the object will be able to handle. And also the quantity of heat in an object, which is represented with Q, is directly proportional to the change in temperature of that object. Let's say theta represents our temperature. That is, the more heat you supply into any object, the higher the rise in temperature that you are expected to witness or observe in that particular object. Now we bring these two statements together, that is saying quantity of heat is directly proportional to the mass of an object and the change in temperature of an object. We can try to eliminate the proportionality there by introducing a constant of proportionality C, and mathematically this C is known as a specific heat capacity of a body or an object. Specific heat capacity of a body or an object. That is a specific heat capacity of a body or an object. Now, what is heat capacity? According to definition, heat capacity by definition is the quantity of heat that is required to raise the temperature of an object or a body by 1 Kelvin or 1 degree Celsius. Let me take that again. Heat capacity is the quantity of heat needed or required to raise the temperature of a body or an object by 1 degree Celsius or 1 Kelvin. So, and mathematically, heat capacity is represented with a capital letter C subscript P, and is always equal to the product of mass of an object and specific heat capacity of an object. Please take note of something here. Heat capacity is represented with capital letter C, while specific heat capacity is represented with small letter c. That is a heat capacity of a body, which is the quantity of heat required to raise the temperature of a body by 1 Kelvin or 1 degree Celsius, is equal to the product of mass and specific heat capacity of the body. So, what is now the specific heat capacity of a body? By definition, specific heat capacity of the body, which is C, which is represented with C, and as we can see here, specific heat capacity of a body, that can be defined as the quantity of heat required to raise the temperature of a unit mass, that is 1 kilogram of a given object, unit mass of a given body, by 1 degree Celsius or 1 Kelvin. Let me take that again. Specific heat capacity of a body is defined as the quantity of heat required to raise the temperature of a unit mass of an object or a body by 1 degree Celsius or 1 Kelvin. That is what specific heat capacity of a body is. So please take note of these two definitions, especially when you are answering a question related to these two definitions in either your WAEC, NECO, or you come across something related to that, or your knowledge is being tested in an examination such as UTME. Notice the little difference between them. Heat capacity is the quantity of heat needed to raise a temperature of a given body, that is, no matter the quantity of that body, by 1 degree Celsius or 1 Kelvin. While the specific heat capacity is the quantity of heat needed to raise the temperature of a unit mass, that is just 1 kilogram of a body, by 1 degree Celsius or 1 Kelvin. So please take note of that when you are defining them, because it is very, very important. Okay, now heat capacity, which is represented with capital letter C subscript P, is measured in joule per Kelvin, while specific heat capacity, small letter c, is measured in joule per kilogram per Kelvin. Please take note of that. Very, very important. So we just need to have this brief introduction before we go straight to the calculation related to this. And this specific heat capacity is what we are going to be laying emphasis on tonight. Specific heat capacity of the object can be determined in different ways. We can determine the specific heat capacity of the body using a method of mixture, that is mixing two substances together, two bodies together. By knowing one of the specific heat capacity of one of them, we should be able to determine the specific heat capacity of the other. And when we do that, that is what we refer to as a method of mixture. Even though we are not going to be analyzing the demonstration, but we are going to solve problem using this method of mixture. And also we can determine specific heat capacity of a body by electrical method, using electrical method. You know that when electrical appliances is used in supplying heat to a substance, maybe for example water, when you boil your water using an electric cooker, the energy from the electric cooker is transformed to heat energy that makes the water to boil. So in that manner we can calculate or determine the specific heat capacity of water by equating the electric energy supplied by the cooker to the quantity of heat energy delivered to the water. Okay, we shall be considering calculations on all these tonight. Okay, now okay, let's go to first example that we have here. Now in our first example, the question says 500 grams of water is heated from 30 degrees Celsius to 72 degrees Celsius. We have to calculate the quantity of heat supplied to the water. Remember from our introduction, quantity of heat represented with Q is equal to mc delta theta. Okay, now and if this is the case, we can easily use this approach in solving this problem. Let's quickly bring out the given parameters in this question. The mass of the water the question is talking about is 500 grams. So let's say our mass equal to 500 grams, and this is equal to 0.5 kilogram. And in this question, we're told that this mass of water, the temperature of the mass of the water is raised from 30 degrees Celsius to 72 degrees Celsius. So we can say the initial temperature of the water, which is theta 1, equal to 30 degrees Celsius, while the final temperature observed, which we can refer to as theta 2, is 72 degrees Celsius. And with this we can determine our change in temperature. Our change in temperature is from 30 to 72, and that will be 72 minus 30, and that will give us 42 degrees Celsius. Okay, that's the first step taken there. And according to the question, we have the specific heat capacity of water. Specific heat capacity in the short form of water is given as 42 joule per kilogram per Kelvin. It's a constant. Specific heat capacity of water 42 joule per kilogram per Kelvin. Okay, and we are asked to calculate the quantity of heat supplied to the water, and the quantity of heat is represented with Q, supplied to the water to raise the temperature from 30 degrees Celsius to 72 degrees Celsius. We can make use of this formula whenever you are calculating the quantity of heat supplied into a substance to raise its temperature. You can easily use this formula here in solving for that. Okay, we can quickly substitute our parameters into this formula by having our m, which is 0.5, multiplied by our c, which is 4200, and our change in temperature, which is 42 degrees Celsius. So therefore our quantity of heat is equal to 88,200. You can easily get that with the help of calculator. 88,200 joules. That's the quantity of heat that is supplied to the water to raise its temperature from 30 degrees Celsius to 72 degrees Celsius. That is first example that we have here tonight. Let's consider another example. During our introduction, I mentioned something, the method of mixture, that is when we have two substances mixed together and the specific heat capacity of one of them is known, we can easily determine the specific heat capacity of the other by using the method of mixture. Now, how do we go about this? Let's quickly check this out in this our second example. Now, in our second example, we have a piece of copper of mass 0.1 kg, and this copper is heated to 100 degrees Celsius and then quickly transferred to a well-lagged copper calorimeter. Copper calorimeter is a container. Okay, and this copper calorimeter is having a mass of 0.05 kilogram, and in this copper calorimeter we have a water of 0.2 kilogram according to the question, and the temperature of that water is 10 degrees Celsius at that time. So we have to calculate the final temperature of the entire mixture. Now what just happened here is that we have a copper metal that is very hot, that is at 100 degrees Celsius, and the mass of that copper metal is 0.1 kg according to the question. This is the temperature. This is the temperature, while this one is the mass of the copper metal, and it's transferred straight away into a container that is copper calorimeter. The mass of copper calorimeter is 0.05, and in this copper calorimeter we have water of 0.2 kilogram, which is at 10 degrees Celsius. Okay, and we have to calculate the final temperature. You will agree with me that when you transfer a very hot object into a cold object, when you mix them together, you know that according to the definition that I stated at the beginning of the class, heat energy is energy transfer from hot object to cold object, not a reverse. It will always move from hot object to cold object, and which means the piece of copper will lose heat to the water. As the heat is moving from a piece of copper to the water, remember the calorimeter, which is the container for the water, will also receive a part of this heat. So we can simply say heat lost by this copper metal is equal to heat gain by the water and calorimeter. Now, how do we present this one mathematically? How do we present this mathematically? Okay, let's quickly look at this. Now, let's QC represent heat lost by copper, that is copper metal, and let's QW represent heat gain by water, and QL, that one represent the heat gain by copper calorimeter. So mathematically, this is what just happened. Heat lost by the copper is equal to heat gain by the water and copper calorimeter. That is what just happened, because when you transfer hot object to cold object, heat is transferred from hot object to the cold object. Okay, let's now say how we can represent this one mathematically. Remember, heat content of object, which is Q, is equal to MC delta theta. Pardon me for this. MC delta theta. And for copper, let's say heat content of the copper will now be equal to, what's the mass of the copper? According to the question, the mass of copper is 0.1, and specific heat capacity of copper is given here in the brackets. We have that as 400. Now, what is now the change of temperature of copper? Remember, we are looking for the final temperature. Let's call it theta F. And if we are looking for final temperature, let's just call it theta. Then we are looking for final temperature is theta. That is what we are looking for. Okay. Now, this is just a general idea. When something is very hot and you transfer it to a cold object, definitely the final temperature will be less than the initial temperature of the hot body. So that makes the change in temperature of copper metal to be 100, which is the initial temperature of the copper, minus the temperature, the final temperature of the mixture. And in doing this, mathematically, we will have this equation turns to something like this. We have 0.1 times 400, that will give us 40. 40 multiplied by 100 will give us, okay, let me just do it step by step. Let's say we have 40 into bracket 100 minus theta, and that will give us 4,000 minus 40 theta. That is for heat lost by copper. The copper metal drops into the calorimeter of water. Now let's check heat gain by water. Let's call that one QW. Still using the same formula, MC delta theta. We can see the mass of water according to the equation. The mass of water is 0.2. The specific heat capacity of water according to the equation is 4,200. And the change in temperature of water, remember the water was at 10 degrees Celsius, and when hot object is dropped into that water, definitely the temperature of the water will rise, and the temperature of the final mixture will be higher than the initial temperature of the water, so that in that case the change in temperature of water will be equal to theta, which is final temperature minus initial temperature of water. Take note of that. And this can give us, we'll break this down. We are going to have 840 into brackets theta minus 10. That is 0.2 multiplied by 4,200 will give us 840. And from here we can have 840 theta minus 8,400 mathematically. Let's check for the heat gain by the calorimeter. Remember, the water is in the calorimeter and the hot copper meter is transferred to the calorimeter. So what will be the heat gain by the calorimeter? We represented that with QL, and that will be MC delta theta as well. And this will be equal to heat, the mass of the calorimeter according to the equation is 0.05. Why the specific heat capacity of the calorimeter? Remember in the equation they mentioned copper calorimeter. Since it is made of copper, it shares the same specific heat capacity as the copper metal. And the change in temperature is the same as that of water, because the water has been in the container and they share the same temperature. So the change in temperature of the calorimeter will be its final temperature that we're looking for minus 10. And from here we can say now 0.05 multiplied by 400 will give us 20. So we have 20 into theta minus 10. And at this point we can open the bracket and have a 20 theta minus 200. And remember initially we said heat lost by copper, which is QC, equal to heat gain by water plus heat gain by calorimeter. So at this point we can bring in every equation that we've been able to generate. Here is heat lost by the copper. Also we have here, we're able to generate this for heat gain by water, and here and here we are able to generate here we are able to generate heat gain by calorimeter. Let's bring them together, and we are going to have sorry for that, I want to use another color for that. Okay, we are going to have heat lost by metal, that is copper metal, and that one is given as we are able to generate that as 4,000 minus 40 theta. So we can easily write that one as saying 4,000 minus 40. So let me give it space so that it will be very clear. 4,000, that is heat lost by copper metal, and that is equal to heat gain by water, which is equal to 840 theta minus 8,400 and plus heat gain by the copper metal, which is equal to 20 theta minus 200. Now at this point we can collect the light times. This is what we have here, so we can collect that, and we have 8,400 on this side. 8,400 minus 8,400 and minus 200 will give us minus 8,600. Taking it to the other side of the equation, we have 8,600 on the other side of the equation. So let's quickly create that by saying 4,000 plus 8,600 will be equal to, now let's sum all the theta's we have 860 theta and the minus 40 theta that is coming from the other side. This one's supposed to be minus 40, sorry for that. It's supposed to be minus 40 theta, not 4 theta, from what we got at the beginning. Okay, bringing this minus 40 theta to the other side, we are going to have 860 theta plus 40 theta, and that will be 860 theta plus 40 theta. Bringing everything together on this side, adding 4,000 to 8,600, we are going to have 12,600 equal to, on the other side, 860 plus 40 will give us 900 theta. Okay, making theta the subject of the formula, we are going to have 12,600 divided by 900, and this will be equal to 14 degrees Celsius. That's the temperature of the mixture we've been looking for. Now what we've done so far, let's quickly run through it from the beginning. In the question, we're given data transfer to a copper calorimeter of mass 0.05 kilogram containing 0.2 kilogram of water at 10 degrees Celsius. That is, hot object at 100 is transferred to cold object, which is at 10 degrees Celsius. Definitely, hot object will lose heat while the cold object will gain heat. That is what happened to the copper, and that is why we have this equation: heat lost by the copper equal to heat gained by water plus heat gained by calorimeter. And we were able to use that approach. Remember, the heat content of an object equal to mc delta theta. We've discussed that during the introductory part, and through that we were able to generate this equation for heat lost by copper, and we moved on to generate this equation for heat gained by water, and we later generated this for heat gained by calorimeter, and bringing them all together in a simple equation that we have here and collecting the like terms, we're able to arrive at final answer by having our theta to be 14 degrees Celsius. Okay, now I talked about the electrical method at the beginning, so let's just look at one more example on electrical method before we call it a day. But before we do that, if you are part of this class tonight and you are yet to subscribe to this channel, please kindly do that so that whenever we are having our subsequent classes, you will be notified. And if you also need a comprehensive note, probably you are in year 10, that is SS1 or SS2 or SS3, and you're studying physics and you need a comprehensive note that can really help you to have the best of the grade that you can ever think of in your physics. A very good note that is summarized and is precise for students. You can check the description of this video on YouTube. You are going to see a link to a note. It's just for a token. The note is compiled and put together for students in SS1 to 3. And if you're interested in it, just click the link in the description. You'll be directed to where you can get the note and just get the note. And if probably you want maybe one-on-one tutorial in either physics or mathematics, that is virtual class on physics and mathematics on Zoom or probably Google Meet or on any channel, you can just check my contact in the description also, and you can contact me using WhatsApp, or you can drop that message on in the comment section, and I will respond to your message. We can agree on a time and just work things out, especially if you are preparing for this year, maybe your UTME, WAEC or NECO. This is the best time to meet with a very good tutor and a professional to put you through with the experience, and you just need a secret to pass all this to pass this exam. You don't need too much hard work. You just need to work very smart. So to work very smart, you are going to need a professional to put you through. And if you really want that in a virtual class through Zoom or Google Meet in any of the two subjects that I've mentioned, that is physics and mathematics, you can kindly reach out to me through the comment section, or probably you can ask for my number at the comment section, or check the description of our YouTube channel. You're going to get my contact there. And like I said earlier, if you need a very comprehensive note to use to prepare for any physics exam between grade 10 and grade 12, that is SS1 to 3, you are going to see a link in the descriptions of this YouTube, or you can just contact me, ask for my number, and we talk on WhatsApp. Also, if you need a very good practical book, one of the best that you can see around now, you can also reach out to me. There's a book called Reform Physics Practical Book, already in use in so many schools in Lagos State and neighboring community in Ogun State. The book is already in use, and the book has been in use for more than 3 years, and people are giving testimony using this book to prepare for practical. It's a teach yourself book that a student can even use without the assistance of a teacher. And you can also go through most of our videos on this channel to get you through some topics that are very difficult. We have videos on so many topics on this channel. Just go through them and watch, even for your practical. And just stay tuned to this channel, and also try and subscribe and click a notification button so that you can get a notification whenever we are uploading a video. Thank you. Now let's go to example 3, which is on electrical method. Like I said at the introductory session, when heat supply to a substance is coming from electrical appliances, we can easily determine the specific heat capacity of the substance by using the electrical energy that is converted to heat energy. Let me quickly take you back to what you will have done in grade 10, probably your third term in grade 10, when you were discussing electrical energy and power. And let me quickly take you through some formulas of electrical energy and power. Remember, then you will have been told that electrical energy E, or work done, is equal to IVT, is also equal to PT. What is I? I is current, V is voltage or potential difference, T is time taken for the power to the time taken to have the appliances working. And also you can as well describe electrical energy as I square RT. One of our videos on this channel talks about this electrical energy and even Ohm's law and some other topics. Also, lastly, for the electrical energy, you can as well have E equal to V squared T over R. R is the resistance of the materials, and I is current, V is voltage, and P is power of the electrical appliances. So any of these four formulas can be used to determine a specific heat capacity of a substance depending on the parameters that you were given in the question. So let's see how we can make use of this. If any part of the video, if you really want to put some things down, you can just pause the video and write whatever you want to write down. So because I want to remove this, and let's go back to what we are actually treating here. Okay, let me do this. Okay, in the question here we have sorry, just a minute, let me remove all this. Okay, we have electrical method, appliances used to boil the water from the question. Okay, sorry for that. All right, let's go back to the question. In the question we have we are to determine how long it will take to heat 3,000 grams of water from 28 degrees Celsius to 88 degrees Celsius in an electrical heater taking current of 6 ampere from 220 voltage source. Okay, now how do we go about this? Let's quickly write out our parameters. In this question, first thing that we have is a mass of water, M equal to 3,000 gram. Okay, the question is, should we take this one to kilogram or not? We may choose not to take this one to kilogram in as much that our specific heat capacity is given in joule per gram per Kelvin. You may not need to convert this one to kilogram, because gram here we take care of the gram that we have as a unit here. Okay, and also we have the θ1 of the water, the initial temperature of the water, as 28 degrees Celsius. We have our θ2 to be equal to 88 degrees Celsius, and according to the question, the current of this heater is this current supplied by this heater is 6 ampere, and the heater is connected to a voltage of 220 volts. So how do we go about this? We are looking for time according to the question. Time is the question, because the question says how long, that is time. Okay, now how do we go about this? In this one we have IVT as the, so therefore we are going to IVT, which is electrical energy. We are going to equate it to the quantity of heat energy supply to the water, and to the water, and with this we can easily make our T the subject of the formula in this equation by saying MC delta theta over IV, and with this we can calculate how long it will take. Okay, therefore we can say our T equal to the mass, which is 3,000. Like I said, you may not need to convert this one to kilogram, because our specific heat capacity of water is given as 4.2 joule per gram per Kelvin, so the gram can take care of gram there, and the change in temperature from 28 to 88 will be 60 degrees Celsius. That is 88 minus 28, that will give us 60 degrees Celsius. Our I, according to the question, is 6 ampere, and our V is 220 volts. So picking up your calculator and press this on your calculator, you're going to have the value of T to be equal to 572.7 seconds. That is how long it will take to raise the temperature of this water from 28 degrees Celsius to 88 degrees Celsius using the heater 6 ampere 220 volts. You can as well have your own question that you've been doing. I would suggest that you pick up your past question, your WAEC and NECO past question or UTME past question. Try as many questions as possible, and if you really need help in handling this, you can drop your question at the comment section. But if you really want a one-on-one tutorial with a professional in physics and mathematics, just ask for my contact through the comment section, or probably check the description of this YouTube channel. You're going to see my number there, and you can reach out to me and we agree on how to go through that on virtual, that is using Google Meet or Zoom, or even any channel of your choice. Also, I said earlier that if you are in need of a comprehensive note in physics that can really help you to pass any physics exam between grade 10 and grade 12, that is SS1 to 3, also you can check the comments, the description section of this YouTube channel. You're going to see a link to Revamp Physics e-note. It's a comprehensive note that covers all your topics from grade 10 to grade 12. And if you are yet to subscribe to this channel, please kindly do click on the subscribe button and click on notification button so that you can get notification whenever we are having live classes like this. And if this video has added anything to you one way or the other, please kindly drop your comment at the comment section as a form of encouragement, and you can also give the video thumbs up. I appreciate you for being part of the class tonight. Thank you, and God bless you.